Hello everyone, this is Xinhao, a PhD student from University of Surrey. Today I'm going to present our paper, an encoder-decoder based audio captioning system with transfer and reinforcement learning, which describes our system submitted to DCASE Challenge 2021 Task 6, Automatic Audio Captioning. This talk contains 4 parts. In the first part, I'll introduce automatic audio captioning task. In the second part, I'll talk about our proposed method. In the third part, I'll talk about our experiments, and I'll present the results and the conclusions in the last part. Automatic audio captioning is a cross-modal translation task. The AAC system received an audio clip as an input and output a natural language sentence which describes the given audio clip. Compared to audio tagging and sound event detection, this task requires detecting the audio events and their spatial temporal relationships and describing the information using natural language. There are not of applications. Automatic audio captioning has attracted increasing attention in recent years, and it was a task in DCASE Challenge 2020. The use of external data and pre-trained models was not allowed in last year's challenge, but allowed in this year's challenge. There are 3 major problems for automatic audio captioning. The first is limited data. The official dataset used in this DCASE challenge is closer. There are just more than 5,000 audio clips. It's really difficult to train a powerful model using deep learning techniques with limited data. And the existing models are almost trained by maximum likelihood estimation. This training method introduces a problem called exposure bias. That is, in the training stage, the word is generated based on the previous ground truth words. But in the test stage, each word is generated based on previous generated word. And this will lead to zero accumulation if the generated word is wrong. And the third problem is the loss function used for ML training is cross entropy, which mismatched with the evaluation metrics, or the evaluation metrics are non-differentiable. Our method is based on the Xi'an transformer network, which achieved the 2nd place in last year's DCASE challenge. The log male spectrogram is used as the input, and the audio features are extracted by a Xi'an encoder. And a 2-layer transformer decoder is used as a text generator. To solve the first data limitation problem, we investigate transfer learning. And this is a cross-modal task where we attempted to transfer knowledge from both audio and text modalities. We investigate 2 transfer learning strategies. First is transfer learning from an upstream task. But using this method, we can transfer knowledge from in the audio modality. But it's not possible to transfer knowledge in the text modality, and the text generator we used is a transformer which contains a cross-modal attention module. And such we investigated the signal transferring methods, which is to transfer knowledge from an in-domain dataset, such we can transfer knowledge in both audio and text modality. To solve the problems brought by maximum likelihood training method, we use reinforcement learning to solve this problem. We regard the evaluation metrics as rewards and directly optimize the model to maximize the non-differentiable evaluation metrics. And the training method we use is self-critical sequence training. In a reinforcement learning setting, the model is regarded as an agent. The words in the vocabulary and audio features are regarded as an environment. The generation of each word is an action of the agent. The parameters of the model is a policy. And the reward is the optimized metric. Here where you choose cider as the optimized metric. And the state is the generated words. The objective function is to maximize the reward of each sentence, each generated caption. The gradient of the object function in this equation, where WS is a sample caption for the model of the model, and W hat is a caption generated by graded decoding at test time. The reward of the W hat is used as a baseline to reduce the variance of the gradient. The objective is to maximize the reward of WS. Only if the reward of WS is larger than the reward of W hat, the weight will be, the parameters will be given positive weight. This is the training stages of the proposed method. In the first training stage, we pre-train the model on audio caps, and the encoder is initialized using pens. In the first stage, we train it on closure. In the third stage, we fine-tune the model using reinforcement learning to directly optimize the cider. If we just transfer knowledge from upstream task, we will just contain the second and third stages. The dataset we use are audio set, close, and audio caps. Audio set is the largest audio event dataset. Close and audio caps are two high-quality audio captioning datasets. The experiment settings are as follows. The batch size is set to 32. The optimizer is add-on. The learning rate is 0.001, and it will be decayed to 0.1 of the CF every 10 epochs. And we train the model for crossing tribe stage for 30 epochs, no matter when pre-train on audio caps or train on closure. And in our stage, we train the model for 60 epochs. And warm-up is used in first 5 epochs in the cross tribe training stage. Spec augmentation and level smoothing is used. If we just use closure, the vocabulary size will be 4,367. If we use audio caps, we merge the vocabulary of closure and audio caps, which gives a vocabulary size of 66,636. And the optimized metric is cider. We compare 5 systems. First one is baseline without using the proposed techniques, and the second is the baseline and use the pens as the audio encoder, which is transfer knowledge from upstream task. And then the third one is use both audio caps and the pens to transfer knowledge. And then the fourth one is the second model, but optimized use reinforcement learning. The last one is the third model, optimized use reinforcement learning. Here are the results. The baseline system can achieve a cider of 0.226 after using pens as an encoder. We can say the performance improves a lot. If we also use pre-trained model on audio caps, it brings slight improvement. The first 3 rows proves that both two transfer learning strategies improve the performance, but pre-trained audio caps bring just a slight improvement. And for reinforcement learning, we can say it significantly improves the water efficiency metrics, although it's was just used to optimize the site. All the evaluation metrics are improved. The resulting system achieved a third place in DCASE 2021 task 6, and it was the best system without using the same technique. But although reinforcement learning improves the evaluation metric, we found it might impact adversely on the quality of the generated captions. Here are some examples. A crowd of people are talking, and in the background, here like something, and also here by on like something, and so the reinforcement learning, although improve the evaluation metric, it might make the generated caption incomplete, and then introduce some wrong grammar, and also after optimizing during reinforcement learning, more than 700 audio clips the caption have in the background, but there are just 155 captions contained in the background before optimizing using reinforcement learning. So for the conclusion, we propose to use transfer learning and reinforcement learning to improve our audio captioning system. And the two transfer learning strategies are proved effective. Reinforcement learning improves the scores of the evaluation metrics. However, it might impact adversely on the quality of the captions. This might prove the evaluation metrics may not correlate well with human judgment. We need to think about some new metrics that can better correlate well with human judgments. The code of our system is available at this GitHub repository. Thanks for your listening.